This video will introduce you to the concept of Bernoulli's equation and how to apply it to different flow situations. What we're considering is elementary fluid dynamics, and what that means is we're considering typical fluid motion in a very basic manner, and by basic manner I mean that we will be applying F equals ma onto the fluid particle's motion using major assumptions. Now, what are these assumptions going to be? First assumption is that the form of Bernoulli's equation that we're going to look at in this video is going to only be for the motion of inviscid fluids. What that means is zero viscosity fluids. We're going to be assuming that there's no viscosity between the fluid layers as well. It's very important to list your assumptions when you're using Bernoulli's equation because these depending on the assumptions that you use, the form of Bernoulli's equation can change, and its application on different flow scenarios will change as well. So the first is that inviscid fluids only, motion of inviscid fluids only. The second is that this fluid motion is going to be governed by only pressure and gravity forces. So when we're going to be looking at forces on this left-hand direction, left-hand side of the equation, we're going to be looking at the net pressure force and net gravity force on the fluid particle. So what that means is, for example, the surface tension effects would be negligible. The third assumption is that we're only going to be looking at steady flow, and what that means is that there are no changes in a fluid property at a given location in time in the flow field. So, for example, if I pick a point, let's say we've got some object here and we've got air flowing around it, and I choose this location and I call this location 1, and I want to see how the fluid properties vary at this location although the time is changing. So the time is moving by, it's changing, and in time at this location, for example, if I'm looking at the fluid pressure, if it remains constant, so for example, partial P by partial Z, partial P by partial T, if it remains constant at location 1, that means that we're going to have a steady flow. And then so on and so forth, looking at different fluid properties like maybe velocity. If you're looking at the change in velocity at this location, then that would be, the change in velocity would be 0 as well. And the last assumption is that we're only going to be looking at 2D flow. So for example, here we've got this axis as the x-axis, and we've got over here the z-axis. Besides the xz coordinates, we're also going to look at another set of coordinates which makes our analysis a bit easier. But before we do that, what we're going to see is that let's just go ahead and look at that figure over here. So we've got motion of each fluid particle that can be described in terms of the velocity vector, which would be v with direction up top. And this is the time rate of change of position of the particle, which is given by ds by dt. Now the magnitude of this velocity vector is simply the speed, but for the direction as the particle moves, so if the particle was, let's say, at location 1, as this particle is going to move, it is going to follow a particular path. And now the shape of this path then is being governed by the particle velocity. We said that we are looking at steady flow. So for steady flow, each particle that is going to pass through this point, is going to pass through this location, will follow the same path that was of the previous particle. So if I had the first particle that is being indicated here, after a certain time has passed, for steady flow, this particle now is going to be, let's say, at this location, and the particle that was behind this at that time is now, when it passes through this, it's going to follow the same path. What that means is that the path is fixed in the xz plane, and then for the neighboring particles, so if we were looking at the particles at this location, it would be the same. The path would be a fixed line in the xz plane, and that gives us an important result, because for steady flow, each particle as it slides along its path and its velocity vector is going to be tangent everywhere to the path. And now the lines that are going to be tangent to the velocity vectors throughout the flow field are called streamlines. So this is, let's say, one streamline that we're looking at. And then the neighboring particles will have their own streamlines. So instead of trying to describe the particles in the xz coordinate system, we can make our analysis easier by describing our flow in terms of these streamline coordinates. So the coordinate that is going to be along the streamline is, let's say, indicated by S, and the coordinate that is normal to the streamline is indicated by N here. And the particle motion now is being described in terms of its distance along the streamline. And we've taken this distance from some arbitrary origin that we've, for example, indicated here. We've just chosen this arbitrary origin. And so the particle motion is being described in terms of the distance along the streamline. This is along the streamline. And it's being described in terms of the local radius of curvature of the streamline, which is being represented by this. So that means that we can write velocity vector, or we can write vectors like acceleration, let's say, in terms of its component in the S direction, which is the streamline direction, and the N direction, which is the coordinate normal to the streamline. So acceleration would have two components then, for example. Got the component that is along the streamline, which is being represented by a subscript S, and then we've got the unit vector alongside it, and the coordinate or the component which is normal to the streamline, a subscript N, along with the unit vector N hat. Now this component over here, which was along the streamline, is known as streamwise acceleration. And the component normal to the streamline is known as normal acceleration. So if we look at the streamwise acceleration first, the speed of the particle is going to vary along the streamline generally. So we can write AS in terms of the change in velocity by change in time. That means we can write it in terms of the derivative dv by dt, and then we can expand this derivative and apply chain rule onto it to obtain a different form of this equation. By expanding, we're going to write it in terms of partial derivative of v to partial derivative of s, because velocity is not only changing in the streamline direction, but it is also changing in the normal direction. So it is dependent on the s component and the n component. That's why we have to write the partial derivative here, and then we can multiply it by ds by dt, which is the definition of velocity that we saw here. Now this component here, this can be positive, it can be negative, it can be zero as well. So that means that the streamwise acceleration, AS, can be positive, which would be acceleration. It can be negative, which would be deceleration, and it can be zero, which would be constant speed. Whereas the normal acceleration comes directly from the concept of dynamics, and it's represented by AN, which is equal to velocity squared divided by the radius of curvature of the streamline. So you can go ahead and review this concept of normal acceleration from section 2.5 in the book titled Dynamics by Merriam and Craig. So these are the basic concepts that you need in order to apply these onto, let's say, along the streamline or normal to the streamline and find out the Bernoulli's equation. And that way, what you would have to do is, for any flow situation, you would have to first of all consider the free body diagram of a small fluid particle. So for example, if you've got this flow field, you would point out, let's say, this streamline, and on the streamline you're going to choose a small particle. You're going to draw the free body diagram of this small particle, showing all the forces that are being applied onto this fluid particle. Remember that the important forces that we are looking at are only gravity and pressure. All of the forces we assume are negligible, like viscous forces or surface tension. So then we first of all look at the small fluid particle along the streamline. And if we were to do that, let's say this is the small fluid particle that we've got. The size of this fluid particle is delta S by delta N. And this is in the S streamline and normal plane. The depth of this fluid particle, or the particle thickness, that means that this is what we are calling particle thickness. Okay, and that is being indicated by partial y. And for steady flow, the sum of forces in the streamline direction, which is the S direction, let's say, which is this direction, we would have to sum all the forces and then equate it to MA. And because we've got a differential element, so the mass of this fluid element is going to be delta M, and the acceleration in the streamline direction is the streamwise acceleration AS. And the forces, because we're looking at the sum of forces in the streamline direction, it's going to be the component, the weight, or the component of the weight force in the direction of the streamline, summed up with the pressure forces in the streamline direction. And then we can equate it to, we already know what the acceleration was, the streamwise acceleration, so we can substitute that here, and that would be V into partial V by partial S. Or we can substitute the mass here using the definition of fluid density. So the mass is going to be equal to density multiplied by the differential volume, and I indicate volume over here by this symbol to differentiate it from the velocity, which is being represented by this symbol. So now what we need to do is we need to find out what these forces are. First, we look at the weight force, and we look at it over here with this triangle given to you. We need to find out the weight force in the streamline direction. So because we've got theta over here, so then this component, first of all, it's in the negative streamline direction, so we're going to have the negative sign here, along with the weight force, which is being given by delta W, along with, because now we're looking at this vertical component of this triangle, so this is going to be sine of theta. And we can simplify this further as well, because we know that weight is given by mg. So that means if I've got the differential weight, then I'm going to have the differential mass multiplied by g. And then here I can substitute mass again using the fluid density definition. So it's density multiplied by the differential volume into g, and then density, which is rho, multiplied by g. Rho g is equal to gamma, which is the specific weight, multiplied by delta volume. Okay, so I can plug that in here, and this would become. And now we can go ahead and we can look at the next component that we want to look at, which is the forces, sum of pressure forces in the streamwise or the streamline direction. Before I do that though, let me explain how the pressure forces act on this fluid element at each face. So if we're looking at this face, pressure force that acts on this face, then assuming that the pressure in the middle of this fluid element is being denoted by P, then the pressure force that is going to be at this face is going to be P minus the change in pressure that takes place as we move in this S direction, so partial P by partial S, multiplied by the distance that we've moved. And because we're moving from the center, the total distance is delta S, so half of that would be delta S and divided by 2. And this is the pressure. To convert it into force, we need to multiply it by area, and the area is going to be the area on which this force is acting, so the area of this face, this entire face, which would be this vertical dimension, which is delta n, multiplied by the depth, which is delta y. So I multiply this by delta n into delta y. So this is exactly what is written over here as well. The only difference is that this entire thing has been equated to differential pressure in the streamline direction. So now I use this pressure force that is acting on this face and this pressure force which is acting on this face to substitute them into this equation over here for the forces that are the pressure forces that are acting in the streamline direction. And because this is the positive one in the positive streamline direction, so I'm going to write this first with the positive direction or the positive sign. And now I can simplify this because this term is going to cancel out with this term, and I'm going to be left with this term now, which is minus partial P by partial S multiplied by delta S, delta N, delta Y. And this delta S, delta N, delta Y is the volume of this fluid element. So I can simplify this further and write it minus partial P by partial S multiplied by the differential volume of the fluid element. And now that I found out the weight force and the pressure force in the streamline direction, I can substitute both of these into this equation over here and simplify it further, and I will get the equation that I'm going to show you here now, which is minus gamma sine theta minus partial P by partial S, which is equal to, from here, rho into, and this gets canceled out, and this term is the streamwise acceleration, so it's rho into AS. And what this equation tells you is that the change in the fluid particle speed is accomplished by an appropriate change of the pressure gradient and the particle weight along the streamline as well. What that means is that if you were looking at a situation where the fluid was static, and that means there was no change in the right hand side of this equation, so this would have been 0, and then the particle would have remained stationary because this force balance would have existed between the pressure and the gravity forces. But in a flowing fluid, the right-hand side of this equation is not zero, so the pressure and the weight forces don't balance each other out. And because of this unbalance, an acceleration is produced within the fluid particle, and that means that the fluid motion is then produced. Now I'm just going to consider this equation, and I'm going to try and simplify it further. I'm going to take a look at a few things here. First of all, along the streamline, from here, sine of theta, I can equate that. And for a differential element, this sine of theta would be equal to dz by ds for a differential element. The second thing is that we looked at the streamwise acceleration, and that was v into dv by ds. But if I wanted to have velocity only in the form of derivative here, then I would have to basically reverse engineer it. And what that means is that I can get this equation if, for example, this velocity as well was within the derivative. It would have been, let's say, derivative of velocity squared by ds. But right now, if I was to simplify this derivative, it would not be equal to this one over here. I need to multiply it as well. So when I simplify it, it would become 2v into dv right now, right? So I need to eliminate that 2, and to do that, I just multiply this by 1 by 2. So now if I was to simplify the right-hand side of this equation, it would become 1 by 2 into v into 2 into dv by ds. So the 2 is going to get cancelled out, and I'm going to be left with v dv by ds. So I can basically write this in terms of velocity squared and its derivative. The third thing is that along the streamline, the change in, or the value of n is constant. So along the streamline, the value of n is constant, which means that dn is equal to 0. And what was n? N indicates the normal to the streamline. So when we were looking at, let's say, pressure, or the change in pressure was dependent on the component of pressure along the streamline. So the component of pressure as it changes along the streamline, partial p by partial s, multiplied by ds, plus partial p by partial n, pressure as it changes in the normal direction, multiplied by dn. And now because dn is 0 along the streamline, then this term is going to be 0. And what that indicates is that the pressure, which is a function of s streamline and n normal, along the streamline, it is only a function of the streamline. And that means that we can write this equation in terms of, mathematically, I'm moving ds onto the other side, so it becomes dp by ds equals partial p by partial s. But what's really happening is that because pressure is only dependent on streamline direction now, so then there is no need for partial derivatives anymore. I can just take the ordinary derivative, dp by ds. And now I can plug all of these into this equation here.